All right, welcome back everyone. I am super pumped to have you here for this completely no-fluff explainer. Today we're jumping straight into the deep end with linear polynomials. Our goal here is simple. We're going to conquer every single theorem, formula, diagram, and example right out of your lecture PDFs. We aren't skipping a single shortcut, we aren't skipping a single test question, and we're following the exact order of the material. So grab your notes and let's get into it.
Here's our roadmap for today. First, an intro to polynomial basics, then we'll hit values and zeros, move on to the remainder theorem, tackle the factor theorem, look at linear growth and graphs, and finally, wrap it all up with a mastery checklist. Let's get moving.
Kicking things off with Section 1, Intro to Polynomial Basics.
So what actually is a polynomial? Well, the name itself kinda gives it away. It comes from the Greek poly meaning many and nominal meaning terms. Basically, it's an algebraic expression made up of variables, constants, and exponents. But listen up, because here is the absolute golden rule. The powers of your variables must be whole numbers. I'm talking non-negative integers only. If you ever spot a square root hovering over a variable, or a variable stuck down in the denominator or a negative exponent, boom, it's immediately disqualified. It is not a polynomial, period.
Okay, check out this massive classification matrix. It's essentially how we organize polynomials, and we do it in 3 distinct ways. First up, by the number of variables, univariate, bivariate, or trivariate. Simple enough, right? Second, by terms, monomial, binomial, trinomial. And finally, by degree, which is just a fancy way of saying the highest power of the variable. A degree of 1 is linear, 2 is quadratic, 3 is cubic, and 4 is biquadratic. But hey, pay really close attention to that middle row. A 0-degree polynomial is just a constant number, like the number 3. But the degree of a 0 polynomial itself, that is literally mathematically undefined. Definitely keep that little trick in your back pocket for exams.
Let's put this into practice and crush a few competitive exam questions straight from your notes. First, an IMO question. A polynomial starting with a times x to the 5th power. Well, it has at most 5 zeros. Why? Because the degree dictates the maximum number of roots. Makes sense, right? Next up, if you subtract a degree 3 polynomial from a degree 4 polynomial, the highest power is still going to be 4, so the new degree? Still 4. Finally, for an equation to truly be a cubic polynomial, the coefficient of the cubed term absolutely cannot be 0. So in that expression, p cannot equal 0. Otherwise, the whole cubic part just vanishes.
Moving right along to Section 2, Values and Zeros of a Polynomial. Finding the value of a polynomial is honestly elegantly simple. It's basically just a plug-and-play operation. You take a real number, let's just call it m, you replace every single instance of the variable x with that number, and then you just do the basic arithmetic. The result you get is denoted as p of m.
Let's look at some specific homework applications to see this in action. Starting with basic substitution, like plugging x equals 1 into x squared minus 2x plus 4, which leaves us with a value of 3. Next, they might throw an area problem at you, asking you to calculate the area of a rectangular park, where the length and width are polynomials, and you just evaluate it at x equals 3. We also see this brilliant little trick from the NCRT exemplar. If p of x is x plus 3, what is p of x plus p of negative x? Well, the x and negative x perfectly cancel each other out, leaving you with just 3 plus 3, which is 6. Super clean.
So this brings us to a crucial concept. What happens when you plug a number in and your final calculated value is exactly 0? Well, congratulations, you've just found what we call a 0 of the polynomial. A 0 is really just the specific input value that makes the entire expression vanish into thin air. And remember that rule we talked about earlier? A polynomial of degree n can have at most n of these zeros.
By setting these equations to 0, we can effortlessly solve some pretty advanced root finding problems. Take the first one. The zeros are visibly 0, 2, and 3. Just look at the factors. But check out that second situation. If you are told that 4/3 is a root, you literally just plug 4/3 in for x, set that whole massive equation to 0, and use basic algebra to uncover that hidden variable k, which works out to be 19. And for the homework problems, setting an expression like lx plus m to 0 allows you to quickly find that x equals negative m over L. Easy peasy.
All right, on to Section 3, the remainder theorem.
Now this is where math gets really powerful. Normally, dividing a huge polynomial by a smaller one requires tedious page-long division. Honestly, nobody has time for that. Enter the remainder theorem. This theorem says skip all of that
If you're dividing by a linear polynomial like x minus a, just take the root a and plug it directly into your original polynomial. The value you get back, that is your remainder. It's an absolute game changer.
We can test this shortcut right now. Look at this NCRT example. X to the 51st power plus 51 divided by x plus 1. Doing that via long division would literally take hours. But using our new theorem, we just plug in x equals -1. -1 to an odd power is still -1. Add 51 and boom, your remainder is 50. Done in 10 seconds. For the NSTSE problem, you just evaluate both equations at x equals 1, set their remainders equal to each other, and solve it to find that a equals -2.
Here is your complete remaining homework matrix for the remainder theorem, and for every single one of these daunting tasks, you apply the exact same logic. You just isolate x from the divisor. So, for example, if the divisor is 2x minus 1, x becomes 1/2, and then plug it right into the dividend. This theorem takes advanced algebra problems and turns them into basic, everyday arithmetic.
Moving right up the ladder, here is section 4, the factor theorem.
The factor theorem is basically the remainder theorem's sibling, and it is elegantly simple. Think about regular division for a second. If you divide a number and the remainder is 0, you've found a perfect factor, right? Well, the exact same logic applies to polynomials. If you plug a number a into your equation and the result, which we now know is your remainder, is exactly 0, then you've conclusively proven that x minus a is a perfect linear factor of that polynomial.
Applying this to your specific NCERT and NSTSE problems, we just test the inputs. For instance, is x plus 1 a factor of x to the n plus 1? Well, only if we plug in -1 and the result is 0. And logically, that only happens if n is an odd integer. For that final question, we just substitute x equals -1 into the equation, set the whole thing equal to 0, and we can easily extract the constant k, which turns out to be 2.
And for these advanced factorization homework problems, you apply the exact same substitution rule. For the first one here, you plug x equals 2 into both equations, set them to 0, and build a system of equations to find that a is 0 and b is 4. You are literally proving divisibility for massive degree 4 polynomials without ever having to draw a long division bracket. How cool is that?
All right, almost at the finish line. Section 5, linear growth, decay, and graphs.
Now we pull these linear polynomials off the page and map them visually. We represent a linear relationship with the equation y equals ax plus b. Visually, that coefficient a is your slope. If a is positive, meaning greater than 0, your line climbs up the graph from left to right. That's linear growth. But if a is negative, less than 0, the line steadily decays downwards. And that constant b, that's just your y-intercept, which is exactly where the line crosses the vertical axis.
Notice how altering that a coefficient changes the steepness of your lines. A slope of 2 is much steeper than a slope of 1/2. But here is what's absolutely crucial for these homework examples. Because the b constant is 0 in all of them, every single one of these lines, whether they are growing or decaying, perfectly intersects the center of the graph. They all hit the origin at coordinate 0, 0.
Which brings up a really fantastic reflection question from your notes. How do you visually differentiate between y equals 3x plus 1 and y equals -3x plus 1? Well, based on what we just learned, both lines are going to intersect the y-axis at +1 because their b value is exactly the same. But because one slope is +3 and the other is -3, they are going to form a perfectly symmetrical x on the graph. One represents steep linear growth and the other represents steep linear decay.
And finally, section 6, our final mastery checklist.
We've reached the top of the ladder, so let's verify our mastery. As promised, we followed the exact order of your lectures. We defined polynomials and their degrees, we learned how to plug in values to find zeros, we conquered the massive shortcuts of both the remainder and factor theorems, tackling all the associated problem types along the way, and finally, we visualized linear growth and decay. You have just conquered every single concept in your linear polynomial syllabus. But I want to leave you with this final provocative thought. If you can graph a linear equation so easily as a straight line, what exactly happens to the shape of the mathematical universe when those polynomial degrees jump to 3, 4, or even 5? Keep studying, and we'll explore that next time.